Happy to have Tudor Dimofte from Edinburgh and UC Davis talking about 3D mirror symmetry and home fly homology.
Thank you so much. And thank you for organizing this online despite everything. I'm going to talk about some work that's sort of been ongoing for embarrassingly 2 years or so with my student Nick Garner, Justin Hilburn, Alexei Oblomkov, and Lev Rozansky. It's sort of related to a wider circle of ideas involving how 3D mirror symmetry acts on extended operators of various kinds, or maybe from a more mathematical standpoint, establishing some homological version of 3D mirror symmetry involving categories and higher categories. The talk I'm going to give today is what I think of as a fun application of a lot of these ideas, and it's teaching us also a lot about what homological 3D mirror symmetry should look like. To paint an overview of the talk, one classic starting point when discussing knot homology in relation to physics involves classic Conifold setup of Oguri-Waffe that then Gukow, Schwarz, and Waffe related to knot homology, and Dunfield, Gukow, and Rasmussen proposed the existence of a triply graded homology theory categorifying the Humphrey polynomial involving counting M2 branes in the resolved Conifold that end on a Lagrangian labeled by a knot or link. And so in the talk today, I'm actually going to take this as my first starting point, and then try to motivate how in a particular case of a so-called tight braid, when the knot or link in question is expressed as a braid that in the limit that the braid stands are very, very close together, and it sort of looks like many, many copies of the unknot twisted up just a little bit. One can compactify this Conifold setup, and the M2s become D2s, and we can look at the world volume theory on these D2s, which is going to be a 3D n=4 gauge theory. And what one ends up with is precisely the setup that Oblomkov and Rozansky have used the past few years in what I'll call the B-twist of this 3D n=4 theory, to give a new formulation of Humphrey PT homology. And their work is based in algebraic geometry and has to do with matrix factorizations, and I will say a little bit about that, but my focus will be more on like what sort of physical setup leads to this mathematical calculation. I should also say that an important motivation in the work of Oblomkov and Rozansky also came from looking at Gukow-Witten surface operators and work that Gukow and Witten done about braiding on surface operators. And so one can get to this 3D n=4 picture also by a reduction of 40 angles with a surface operator. That is another way to get to the same thing. And then hopefully I'll get a chance to talk about the new stuff, which is applying 3D mirror symmetry to this whole construction. We're applying 3D mirror symmetry not just to the bulk theory, which ends up being a theory whose Higgs and Coulomb branches, well, it's the ADHM quiver theory in the bulk. Higgs and Coulomb branches are both copies of the Hilbert scheme. Applying 3D mirror symmetry to that bulk theory is easy and well known, but then we need to apply it to to a boundary condition and a certain line operator sitting in the middle. There are many ingredients in this setup. And we can do all that and then ask a question again about what the Hilbert space on a certain solid cylinder is. That's how this knot homology appears. The calculation looks very different. The B twist has become an A-type twist. And a nice surprise in the end was that at least for a certain family of so-called algebraic knots, what we get actually reproduces a conjectural computation of the Humphrey by Gorski, Oblomkov, Rasmussen, and Schende involving affine Springer fibers. And so there's a really nice connection to that. And as I said, many of the tools for understanding this 3D mirror map have come from some recent work of myself and others. Especially like the recent things especially involve understanding what's happening on the A side. Okay, so let me start with a very brief review of the Conifold setup and start compactifying from there. So the resolved Conifold can be thought of as a Kähler quotient of C4 with a U1 action that has weight 1 on 2 complex coordinates and weight -1 on the other 2. Algebraically, that's equivalent to a C star quotient of C4 with the locus where the first 2 coordinates, x1, x2, are 0 is removed. And so the details here are not super important. The resolved Conifold is a C2 bundle over P1. And the story I'm going to develop sort of all happens in a neighborhood of the north pole of this P1, where locally we can just think of this as C3. And so there's a U direction. Well, the direction I'm calling U is very close to the North Pole along the CP1. And then there are fiber directions W and Z. The compactification I'm going to try to do involves a U1 action that rotates these coordinates I've called x1 and y1 in opposite directions. So what it does is rotate the CP1, and it rotates one of the fibers above the North Pole. And after we transport that rotation to the South Pole, it ends up acting on the other fiber. But one of the copies of C at the North Pole is invariant, and one of the copies of C at the South Pole is invariant. So the Z direction isn't being touched here. Right, so if we did simply that compactification in the neighborhood of the North Pole, this U1 action I'm using has a fixed point, and that leads to a D6 brane in type 2A theory. Now, just the bulk geometry is not enough to get knot homology. The geometry of a knot or link is encoded in a Lagrangian in the resolved Conifold, and in M theory, one wraps M5 branes on this Lagrangian. The construction of this Lagrangian involves starting with the deformed Conifold T star S3, where it's the conormal bundle of a knot. And Witten showed a long time ago that, well, in this case, things are related to Chern-Simons theory, and then Aguirre-Vafa described these Lagrangians. Anyway, after going through a Gopa-Kumar-Vafa large N transition, this conormal bundle of the knot becomes some Lagrangian in the resolved conifold that's been described in greater and greater levels of detail and generality. The construction we actually used when we're trying to be careful about this appeared in a paper of Diaconescu, Shende, and Vafa some years ago. The topology of this Lagrangian, for what it's worth, is S1 times R2. And the things that give you knot homology are M2 branes. So in knot homology, one is looking at BPS states of M2 holomorphic disks that end on the S1 in this knot Lagrangian. That is most of the story. However, for triply graded homology for Humphrey, one needs an additional grading, an A degree. And did I write that in? I didn't quite write that in. I'll talk about that in a second. I wanted to say a bit more about the M2 disks first. So before getting to A degree, this Diaconescu Shende Vafa construction is especially nice in the case of what are called algebraic knots. And I'll revisit algebraic knots at the end of the talk because they're also especially nice in the A side field theory construction. So an algebraic knot is a knot that comes about as the intersection between an S3 inside C2 and a plane curve, typically a plane curved singularity, written as the solutions of some polynomial equation P of W and Z equals 0. And so, for example, if you want to describe the unknot this way, there are several different ways to do it. You can just take the equation W equals 0 and intersect that with S3. And I wrote Aganagic Vafa next to that because there's Aganagic and Vafa wrote down a family of sort of famous family of toric Lagrangians in the resolved conifold, and it's one of those Lagrangians that are relevant for this case. But there are several other ways of representing the unknot. And if you want the trefoil, you can take the polynomial W squared minus Z cubed, for example. But there are multiple ways of representing any knot like this, any algebraic knot like this. The really nice thing about the Diaconescu Shende Vafa construction is that the Lagrangians LK they write down are precisely such that the M2 holomorphic disks related to an algebraic knot wrap these curves P equals 0. The Lagrangians themselves are actually horrendous to write down explicitly, but the M2 branes are really nice, and so they just wrap these these singular curves in the C2 fiber above the North Pole in the resolved conifold. Okay, and then I'll say the final thing about A degree. So to get higher A degrees in Humphrey homology, which splits by A degree, there's an additional thing one can do, which is to add extra M2 branes wrapping the compact P1. And so if you want the A to the K part, if you want to categorify the A to the K part of the Humphrey polynomial, you add K extra M2 branes wrapping that compact P1. So, so that's the geometry with all the bells and whistles. And now we can ask what happens if we do that circle compactification that I discussed before. Assuming that the knot is sort of the form I described, where it's approximately the unknot sort of wound around itself many times with a bit of braiding, then our M2 disks are also going to be multiply wrapped disks. So if I express this as a braid on n strands, then I have an M2 disk that is wrapped n times. And after the compactification, this becomes n D2s. The D2s end on a stack of NS5s. So the M5s that had been wrapping the knot become NS5s. And there's a little caveat I should throw in here. If you use the Algebraic Knot Lagrangian, you don't actually get this. You do the compactification and you end up with D4s. But as long as you deform this Algebraic Knot Lagrangian just a little bit, as for example in the Diaconescu-Schende Waffe, then you get NS5s. And so you end up with locally with a really sort of familiar brain construction of a stack of D2s ending on a stack of NS5s. Everything is in the background of a D6 coming from that north pole of the P1, where the, which is a fixed point of the rotation. And the extra M2s that were wrapping the P1 now just become strings that sort of intersect the D2s along a line. And we can translate that entire thing to field theory. So if we focus on the world volume of what had been the M2 brains, now they're D2s. A bunch of D2s sitting inside a D6 give us the ADHM quiver. So this is the classic construction of instanton moduli spaces. Here it's abelian instantons. So because there's a single D6, so we get a 3D n equals 4 theory whose gauge group is UN, and whose matter, whose hypermultiplets sit in a quaternionic representation T star V, where V is the Lie algebra of GLN and a copy of C to the n. In other words, an adjoint and physics terms, an adjoint and a fundamental. The Higgs branch of this theory is the Hilbert scheme of endpoints on C2 once it's been resolved, and so is the Coulomb branch. And it's maybe worth pointing out that the C2 in this Hilbert scheme, in this Coulomb branch Hilbert scheme here, is literally the U and W direction in the resolved Conifold. So this 3D field theory is living on disk times time, and it's got an interesting boundary condition. That's again a familiar boundary condition. It looks just like a reduction of the T of G type boundary conditions for the Yang-Mills that Guyotto and Witten wrote about. In sigma model terms, I can describe the boundary condition as coupling the bulk theory to a copy of a T star flag sigma model. Flag is the flag manifold for GLN. And the coupling involves a certain superpotential that combines one of the adjoint fields of the bulk theory and the complex moment map for the UN action on the flag manifold. Perhaps the most important thing to say about this boundary condition is how it actually encodes this braid. So the braid is coming from the Lagrangian and the Conifold, which turns into positions of these NS5 brains after we compactify, which turns into, in these positions, become a bunch of complex Fi parameters. They are two-dimensional Fi parameters on the boundary, and they're literally resolution parameters of this flag manifold that's appearing. And each of these complex Fi parameters is telling you the location of a certain strand of this braid. And as we go around the boundary, the Fi parameters can move, and this motion encodes the actual braid that we have. So finally, there are the extra M2 branes on the P1, and they compactify to a fundamental string, and they give rise to a Wilson line operator. And it's a Wilson line. In the gauge theory, it's in the kth exterior power of the fundamental representation, or if you want to think of it as sort of on the Higgs branch, that ends up describing a certain bundle on the Higgs branch, which is just the kth exterior power of the tautological bundle of the Hilbert scheme. So, so those are sort of the three ingredients in the field theory. And then knot homology is supposed to come about as the BPS Hilbert space of this theory. But we can't just say BPS because there are a lot of different BPS things in 3D n equals 4. We have to be a little bit more precise about what sort of BPS states we actually want to look at. And the answer, going more carefully through this, is that it's the Hilbert space in the 3D topological B-twist. And at this point, I need to have a little digression into topological field theory in 3 dimensions. So first, all 3D n equals 4 gauge theories admit 2 topological twists, and sigma models admit these twists, but with certain constraints that are beyond the scope of the present talk. So I don't think they were historically called A and B. Quite a few of us are calling them A and B now. The reason I call them A and B is because they're directly analogous to A and B twists in 2 dimensions. They're in fact directly related to A and B twists in 2 dimensions upon further compactification. And they are exchanged by 3D mirror symmetry, just like 2D mirror symmetry exchanges A and B twists in 2 dimensions. To orient folks a little bit, the A twist is a reduction of the 4D Donaldson-Witten twist. Various aspects of it have been studied over the years. It was some versions of the A twist and sigma models were described by Kapustin and Bias. Telemann described aspects of the relation between 2D mirror symmetry and 3D mirror symmetry, and evolving in a significant way is 3D A twist. And this is important in recent work of Braverman, Finkelberg, Nakajima, and Coulomb branches, and the more recent things collaborators and colleagues and I have been doing involve describing categories of line operators in the A twist. The B twist was first observed to exist by Blau and Thompson, and it played a major role in work of Rosansky and Witten. This is the B twist of sigma models. And Kapustin and Rosansky and Salina described higher categorical structures in the B twist. In gauge theories, there are surprisingly intricate features that appear that are being studied with cutting edge derived algebraic geometry nowadays. This is work of Hilburn and Yu and Hilburn and Sam Raskin that's ongoing right now. I won't need any of that for this particular application. So second part of the aside, So first, there are these A and B twists in 3 dimensions. Some things about them are understood, a lot is not, especially at categorical levels. So the second part of the aside is just roughly what one expects from any 3D extended TQFT. There are 2 ingredients that are important for the current application. One is the category of line operators in the bulk, and one is the 2 category of boundary conditions and line operators on that. So in the bulk, line operators form a braided tensor category, just like they do in Chern-Simons theory, except it's going to be some DG version of a braided tensor category in this case. Boundary conditions should form a 2 category, and the aspect of that that's quite important here is, given a fixed boundary condition, one can consider line operators sort of bound to the boundary, self-interfaces of that boundary condition. And these line operators bound to the boundary, called endomorphisms of that boundary conditions little b, form a tensor category. And it's a tensor category just because these self-interfaces can be collided with each other. And that's the tensor product. There are 2 operations that relate, line operators in the bulk and line operators on the boundary. Given a bulk line operator, one can bring it to any boundary condition. There's a bulk boundary map. And yeah, I've sort of written mathematically what that is. So that's a functor from the bulk category to, in fact, the center of this monoidal category of endomorphisms on the boundary. And there's a map the other way, which says, given any boundary condition, wrap it on a cylinder. So consider a theory that has sort of a solid cylinder drilled out with your favorite boundary condition on it, and you can enhance that by using a self-interface, which I called beta in this picture. And if you zoom out, then from far away, this looks again just like a line operator. And so this wrapping on a circle is a way to take a boundary condition with interfaces and turn it into a line operator. Okay, so that's the end of the aside. These operations and these categories end up being relevant for computations in the A twist and the B twist. In this work of Oblomkov and Rosansky, which I should say is also closely related to work of Gorski, Negutz, and Rasmussen, involving Zorgel bimodules. Anyway, in Oblomkov and Rosansky, one has a 3D n equals 4 theory, gauge group UN, representation, adjoint plus fundamental, Higgs branch is the Hilbert scheme. The category of bulk lines is, in the full gauge theory, is some horrible thing, but if we turn on a real Fi parameter and resolve the Higgs branch, it just maps down to coherent sheaves on the resolved Higgs branch, which is the Hilbert scheme of endpoints on C2. Then I said before that that line operator we had stuck in had to do with exterior powers of the tautological bundle. Now I literally mean that as a coherent sheaf. So as an object in the category of bulk lines, that line operator in the middle is the kth exterior power of the tautological bundle. And then Oblomkov-Rosansky very carefully identified what the monoidal category of lines stuck to the boundary was, and gave it a description in terms of some matrix factorization category where the tensor product comes from convolution. And again, the details here are extremely interesting and not important for this talk. The important point is that there is a representation of the braid group inside this category of line operators on the boundary, which literally comes from the fact that physically you have these complex Fi parameters and you can just move them around each other. Moving them around each other very quickly creates a line operator or a self-interface on the boundary. And that self-interface is an object of this category. And so the braid group gets represented in the category of lines on the boundary. Then you apply the compactify and S1 map to turn a boundary condition with a bunch of braiding interfaces into a coherent sheaf on the Hilbert scheme. You turn it into a bulk line operator, and then just compute derived HOM between this bulk, derived HOM between this bulk line operator and the thing that was counting a degree and the exterior power of the tautological bundle. Let me just give a picture of what that looks like in physics. So we're trying to find the Hilbert space of a theory in a solid cylinder. It's got a line operator in the middle, and it's got a boundary condition with a bunch of line operators on it on the outside. We can use a state operator correspondence. We sort of peel the boundary of the solid cylinder away and down, invert this entire picture, turn the boundary into another line operator. And that's this Chern character map, the compactify and S1. So now we have sort of a very, very thick line operator coming from this wrap boundary condition with a braid interface. And we have our very simple Wilson line, LK. And the Hilbert space on the left has become local operators at the junction of this Wilson line and this very thick boundary condition. And computing local operators at a junction of two lines is what derived HOM or Ext in the category of coherent sheaves does for us. So this is at least one way to get the answer, and is one way that was just made very explicit in the mathematical work. Great. So, so now let me go through a few pieces of the 3D mirror construction. I may even finish before time is up because I've been going too fast, fearing that I would run out of time. So the mirror of the bulk theory is itself. This is very famously self-mirror. A case of this was described in the original work by Interligator and Seiberg. And in terms of brain constructions, this was in work of Debord, Horiogori Ozanyan from the mid-90s. The thing that's changed in the mirror is that the Higgs and Coulomb branches have swapped. In particular, now the Higgs branch, which is sort of parameterized by eigenvalues of the adjoint X and Y fields, corresponds to the U and W directions literally in that resolved conifold picture we had at the beginning of the talk. The boundary condition can also be analyzed through a local brain construction. And unsurprisingly, to anyone who's learned about S-duality of boundary conditions in 4-Vieng knows, the mirror of that seemingly complicated T-star flag boundary condition is pure Dirichlet. It's a boundary condition that simply breaks the gauge group at the boundary and fixes half of the hypermultiplet fields. And here it's fixing it's fixing x and, well, one of the adjoints and one of the fundamentals, the complex Fi parameters that were resolutions of this flag manifold have now just become fixed eigenvalues of the adjoint field x at the boundary. So this is just phenomenally simpler than what was happening on the other side. And the braid, again, comes from taking this local boundary condition and changing it as we go around the circle. And so we'll just braid eigenvalues of our x field. There is also this line operator going through the center of the cylinder. And to say what it is, I need to say things in categorical terms. And so I should tell you a bit about the category of bulk line operators in the A-twist, which, the way I've written it here, looks maybe horrendous. Physically, what you would want to say is that this looks like some sort of Fukaya category on the loop space of the Higgs branch. And here I've given you a mathematical description of it that seems to be leading to sensible calculations. So this is an algebraic description where we take the algebraic loop space of not quite the Higgs branch. One needs to remember that this is really a gauge theory. And so it's, the way I've written it is in stacky language, and I think the details are just not sufficiently important right now. But this is a thing that makes sense mathematically. Or you can think of it as strongly equivariant D modules so equivariant for the loop group on the loop space of the matter representation. And because we've gone from something Fukaya-like on the entire Higgs branch to D modules, we should be just looking at sort of the base of the cotangent bundle, and so this is why I only have half of the representation there. It's only half of the hypermultiplet fields that are around. Look briefly at the audience. I think there are probably more physicists out there than mathematicians, so let me also just say physically what's happening. So in the line operators in the A-twist are vortex lines, and they're typically disorder operators, and they're described by giving a holomorphic singularity to fields in the plane transverse to a line. And objects in this fancy category involving a loop space can precisely encode either poles or zeros in various hypermultiplet fields as we get close to the line. And I am going to run out of time. Anyway, the mirror of the Wilson line can be analyzed using brain constructions that were described by Assel and Gomis, and then we explained with Garner, Gerasi, and Hilburn how to translate that to an object of this fancy D module category. I'm just going to say right down that it can be done, and roughly what it does is to give a 0 to k rows of the x field and to give a pole to k columns of the y field as one gets close to the line operator. And then there's, so I think I've actually described everything. And then what's left to do is a computation of this Hilbert space on the solid cylinder. And the computation is really beautiful in the special case of what are called positive algebraic knots. The algebraic condition is just so that we end up with an algebraic object in this category of D modules that's described algebraically. Otherwise, one has to do more work. The positive condition is a technical thing, and it has to do with yeah, not going to have time to talk about it now. But what is one of these things? Yeah, I should finish up. I'll just say this very quickly. So when one takes a knot described by say a plane curve singularity, expresses that plane curve singularity as the characteristic polynomial of some matrix, and then that matrix is literally going to encode for us the boundary condition. You take this variable z restricted to the unit circle, and now you've got what your x field is fixed to all the way around this solid cylinder. And then there's a calculation. Apply this categorical turn character map, get down to the category of D modules. And at the end of the day, you're computing a hom of D modules, which ends up being homology of a certain moduli space. That's an extremely concrete mathematical thing. Also physically, this is counting vortices. So the Hilbert space in the A-twist of this 3D n equals 4 theory is the cohomology, is the de Rham cohomology of vortex configurations, of the moduli space of vortex configurations on this disk, with a certain singularity at the origin and a certain boundary condition along the outside. This is just a way of making that mathematical. And I will say the final thing, which is that this is a conjecture for Humphrey homology, but it is in fact provably related to another known description of Humphrey homology. And so my student Nick Garner and Eugene Gorski's former student Astrid Kuvinen actually wrote a paper, and they're writing another one, proving that this moduli space that shows up in this computation is the same one as that appeared in work quite a few years ago by Gorsky, Blomkopf, Rasmussen, and Chende, involving affine Springer fibers. I take 10 seconds to conclude. So there should be, this isn't far from the end of the story. For non-algebraic knots, one needs to actually figure out a braid representation in some A analog of the matrix factorization category that Blomkopf and Rozansky had. This is interesting and very much in progress. It looks like there is some Fukaya-Seidel category involved. And let me just come back to an initial motivation for all of this. So in many ways, for me, this is a fun application of a broader set of ideas, and these examples relating to not homology, which are things things one knows, or at least concrete things to connect to, are really teaching us important lessons for how 3D mirror symmetry should act on things like two categories of boundary conditions, which I think is interesting and very much open still. Thanks.
Thank you. If someone can unmute people, because I don't seem to find out still how it is. I guess not so. Yeah, so then thank you. And then now we can mute all.
Oh no, sorry, Ines, you've been muted yourself.
I unmuted you and I forgot to unmute myself. Yes, so we already have one question by, sorry, I can't say your last name, Aswin.
Hi, yes.
Yeah, that's okay. Yeah, hi. Hi, Tudor. I had a question. So what is the compatibility condition between the choice of the Gukov-Witten surface operator and the 3D n equal to 4 theory? Should the corresponding T star flag manifold be related to the Higgs or Coulomb branches in any way? Or
and of course there are lots of dualities there. So it depends what side you're working on. But yeah, so So you can start in 4 dimensions with, sorry, the compactification we're doing, let me just say that, is a circle compactification in the plane transverse to the surface operator. So locally, we have a surface operator in 4D, and transverse to it is a plane where the surface operator is at the center. And then we're doing a circle compactification on a circle that is contractible. So locally, when we do that, we will end up with a 3D theory on a half space, on a 3D theory where the surface operator from 4D has become the boundary. And there's a way to globalize this. And if you want knot homology from a Gukow-Witten scenario, then you have to put your surface operator on a circle, and it's all sitting inside a 3-sphere. And then you do this compactification, and you end up with the solid cylinder in 3D. That's describing the geometry. Otherwise, it's the same sort of thing. So Gukow and Witten precisely coupled to like T-star flag to describe their surface operators in n=4.
But then is T-star flag some kind of subspace of either the Coulomb or Higgs branches? Is that the way to think about the boundary condition? No, it's not. Okay.
No, it's not. In general, on a boundary condition, you can introduce any 2-dimensional theory whatsoever. That has the right supersymmetry. And then you couple it to the bulk by introducing things like superpotentials or gauging part of the boundary the boundary flavor symmetry with bulk gauge symmetry. So yeah, it's not. You should think of this as a higher dimensional analog of a Chan-Paton bundle. If you have a boundary condition for a 2-dimensional theory, you can tensor it with a vector space. That's the Chan-Paton bundle. And so here we're tensoring things with T-star flag.
Thank you.
Yeah.
Thank you. So we have another question from Sergei Gukov. Can you unmute yourself?
Yes, I think I can.
Yes, you are.
Hi, Tudor. Thank you for a very nice talk. This was quite a story. I have a very lowbrow question, as Nadia would put it. Suppose we change framing of a knot by 1 unit. So how does homology change, and how do we see this in the physics of line operators that you described?
It's not in the line operators. It's going to be in the boundary condition, and I am honestly not sure. I think for the A-side calculations that worked out, there must be some canonical choice of framing on these algebraic knots. Otherwise, it had better be part of, what you would expect is to find a line operator on the boundary that changes framing on a strand. And so in the matrix factorization category that Levin and Alex use, they must have something like that. And I don't know. But it, as you point out, it has to be there since these are invariants of framed knots. And it had better appear in this sort of Fukaya-Seidel category that has a braid group representation on the A side as well. Yeah, that is, I don't think that's a lowbrow question. That's an interesting thing that we need to figure out.
Okay. Thank you. I think we have one other question from Mina Ganajic. if you want to unmute yourself.
Okay, yeah, I managed to do it. Thank you, Tudor, for a wonderful talk and a wonderful story. I have one question about the comment that you made about the relation, whether the boundary condition is an NS5 or a D4 brane boundary condition.
Yeah.
Within the Calabi-Yau threefold, I don't think there's any room for this kind of deformation. Simply because the M5 brane is occupying simply all the circle symmetries. So could it be that what you're doing is somehow pushing the M5 branes very, very far at infinity, where at infinity, you don't really have a Calabi-Yau threefold, you have a smaller structure. In other words, it's almost like a twofold times C star. And that's where the whole story happens at infinity, not. So your M5 branes can never ever be, you can never push them close to the conifold. They're always far at infinity. Where at infinity, it can be essentially holomorphic.
That may be a useful thing to do regardless. I think it's easier. So in general, one of these Lagrangians associated to an algebraic knot, if the equation P of ZW equals 0 has a symmetry, and often it does, then the Lagrangian can also be engineered to have that symmetry. But that's almost never the U1 that I'm using to compactify. And so unless you are silly about it and use the wrong version of the unknot. So the one case where they do coincide is for the simplest version of the unknot, W equals 0. But if you use W equals Z instead, then the symmetry that preserves that is not the U1 symmetry.
So which U1 symmetry are you using?
So
I think we've used up all of them.
I did not. So there's because. Okay. So I'm using a U1 symmetry that leaves one of the copies of C above the North Pole alone entirely, and it rotates the other copy. And so this is a specific choice. And these Lagrangians are often invariant under a U1, but it's a different U1. And so upon this other U1 symmetry just rotates them around, and it doesn't leave them invariant. And so I think in general one does get NS5s.
Could you just briefly repeat again which U1 symmetry is it? Because
sorry,
say it one more time, maybe I would.
So it's a U1 that rotates the P1, and it rotates one of the fibers above the North Pole, but not the other one. In particular, the fiber it doesn't rotate is the same as the Z that shows up in vortex counting on the M2 branes. I think the relevant thing is that there's just one copy of C that is preserved pointwise.
There's something that bothers me about this, but okay, fine. I don't think I can complain in real time. So go. I'm sure your story is correct. So the only question is perhaps how it is correct. But
I'm quite happy to discuss this in more detail and make sure that everything fits. Yeah.
So thank you. So there's one last question before we go into the breakaway rooms. We're basically out of time in any case. So, well, I would like to thank both the speakers, both Eric and Tudor. Thank you for the very nice talks. And I think there'll be now time for actual long discussions.
Thanks, Ines. Thanks, everyone.
And so I don't know how it's going to be now. Is everyone going to be split?
Ines, I'll
yes,
thank you very much. Very good. Thank you, Ines, for chairing the session, and thank you to the speakers of the session. I have requested in the chat for anyone who has a preference for which session to join. I'm going to give it a few more minutes and then open the room at rooms at 7 p.m. That's in 5 minutes my time. The rooms will remain open for an hour. We'll start, and if the discussions go on further than that, then tomorrow we'll extend it, etc. But for today, I'm going to start off by opening them for an hour. I have broken the rooms up into 2 rooms for session 1, which were the first 3 talks, and session 2, which were these last 2 talks. And the speakers for the sessions were automatically assigned to those rooms. And I have requested in the chat, if anyone wants to move into any particular room, please send me a private message. And the only content that needs to be there is session 1 or session 2. And I will move you in there, and then I will open the rooms. If there's no preference indicated, I will leave you in the main room, and you can always ask me a little later where to move you. You can also move between rooms should you want to. Again, just send me a message. Let me ask again, if you have any preference, to please send a private message to me in the chat room. If you're a speaker, you don't need to, for today's sessions, you don't need to tell me, you will automatically put into your session. So in 5 minutes, I will open up the sessions and you will get an invitation to go to a particular room. Thank you.